Welcome back. This is session 3 of OpenCV 101, a practical guide to the Open Computer Vision Library. I'd like to thank our sponsors once again, LLNL Engineering, CASIS, the Center for Advanced Signal and Imaging Sciences, as well as our joint sponsors, the Oakland East Bay chapter of the IEEE Signal Processing Society. So we got multiple fun topics to talk about today, including feature finding, segmentation, and transformations. If you haven't already, I've put up some new files on the GitHub repository. So if you go to github.com/mrever and navigate to the CASIS OpenCV course, the main file that we're going to need is the notebook, of course, CASIS OpenCV course session B. And I've put a few new files and data, and I've checked this time, they are actually there. Not like last time, but the new files are coinsb.jpg, as well as messymask.png. So we're going to use those in our examples today. All right. Let's go into notebook mode. So first topic we're going to talk about is image segmentation. So what is that? Image segmentation is where you take an image and you split it up into regions of interest. So generally your scene, your image will have multiple objects of interest, and you want to know where like one object begins, one ends, where does the background begin and end. So what you want is an output image of the same dimensions as your input image, but your output image is going to be labeled into, like, say, region 1, region 2, 3, depends on how many segments you want. An example of that would be like, if you took a picture of my face like against this background, you might label my face to like region 1 and the background region 2, for example. All right, so remember our utility commands. So the first thing you're going to want to do is execute these commands right here: PyLab notebook, import CV2, and of course you need to navigate to the directory where our data is. So for me, I'm just changing directories there, but I assume everybody can navigate as appropriate on their own machine. All right, so the first algorithm is called the watershed algorithm. It's so called because you can kind of think of any image as a topographic map with depth to it and height to it. So if you take regions of similar color value, similar intensity, texture, or whatnot, you can think of that as like a constant height value. Then if you know ahead of time like which regions correspond to what you want segmented, not completely segmented, but some sort of markers, you can start filling in the regions until they start to meet each other, and then those are going to define the boundaries of where your image segments are going to meet. So if you want to learn more about the algorithm, you can check out this website right here, and it contains nice description of what exactly is going on, and it's got some animations and so forth. But again, this isn't really so much a theoretical course, so there's going to be just going to give like little qualitative explanations and just show you how easy it is. We're going to do simple examples, just show how easy it is to actually use these in your own code for your own applications. So first example, we're going to question. Do we have the microphone? Let's see if, just want to make sure the people watching at home later can hear.
So is this a different set of algorithms from boundary finding algorithms, or are they the same sort of idea?
So your question, is this different from boundary finding? Are you asking like the edge detection like we were doing before?
Yeah, exactly.
So yeah, this is distinct from edge detection. Edge detection is strictly the boundary, strictly where there's a separation. With image segmentation, you kind of fill in the gaps. So the thing is, with edge detection, you might find an edge, but the edges aren't necessarily closed. They don't necessarily form a continuous loop. Whereas segmentation will actually find an entire boundary where there's a transition. So they are related. Edge detection could be used for segmentation, but it is distinct in that sense. All right, so here's our code right here. I recommend just running it first, and then we can see the results below. So we're going to operate on our image of coins right here. So in this case, I said before that we have some predefined labels for our images to start off with. In this case, we're going to define those programmatically, but in general, you do want to label them. You do want some sort of labeling. So we have this image of coins, and you can see each color here corresponds to a different segmented region. So how does this work? All right, so we start off with our coins image right here, which we see on the left of our figure below. And then we want to operate on grayscale, and we're going to threshold out just regions. This isn't getting exactly what we want, but it's just kind of a guess, a kind of an initial assumption that's going to help us do the segmenting later. And then we remember our morphology operations. This is one that I didn't cover last time, but it's still pretty simple. This is opening. This kind of tries to break up binarized images into distinct regions, even if there is a little bit of touching. So we threshold our image, we break it up, we dilate it, make sure, in this case, our background area is what's going to be expanded, because we just want to make sure that we're separating, like you see these two coins that are touching right here. We want to make sure that those are separate. So we dilate our background area. Then to get our foreground area, we're going to call this distance transform function. What that is it starts from, you have a binarized image, and you want to compute the distance from where you have zeros from where you have ones. So the output of this is going to be another image where each pixel value is the distance from whatever region of interest. Then we threshold that out to see where the distance becomes so far away, which will get us our foreground or our coin area. And we make sure that we're going to have some blobs right where our coins are. Then we do some subtraction, make sure we know where, kind of where the borders are. And then to do our initial labeling, we use this cv2.connectedComponents. And what that's going to do is, just kind of make everything that's connected equal to the same value. So that's a good way of separating out your images. But that's still not the segmentation. That's still just kind of a crude estimation of what's what. This is just so that we can feed it into the main piece of our code, which is watershed right here, which takes in our original image as well as our markers, which is kind of a crude estimation of where each image is. And then that's going to give the output markers, which is this image you see here, which is colorized per object. So realize that's a lot to take in all at once, but again, this is kind of a survey, so hopefully you guys should play with this on your own, and then you can see how it works and see how to apply it towards your own applications. Then one of the other major algorithms for segmentation is known as the grab-cut algorithm. And there's a lot of neat theory on this based on a graph theory. Too much to get into in a course like this, but I do recommend reading up on it later. You can learn a lot about the theory behind it, and it is useful for application later. But grab-cut, you're generally going to, in order to use this, what you're going to do is you're going to start off with your image. So we're going to use this messy image, the soccer player right here. We draw a rectangle around this guy. Actually, you know what? I'm going to go ahead and run this right here. So where are we? So that's going to pull up these images right here. So what we do, some instructions should pop up on your screen. I'm going to draw a rectangle here. It's going to get your initial guess of what it is you're trying to segment out. So we've got our guy here, but we're kind of cutting off his hair, we're cutting off some other parts. So then we select 0 to select what our background is. We can draw here, here, here. Press N to update. Then press 1 to get our foreground here. Let's draw on his hair, so forth. Then we get his hair. So the version I put up there is actually, in the repository, is actually a modified version, which is going to save the mask that we drew to disk. So I'm going to break out of this. And just to see, I do recommend going through the grab cut example that's in your Python directory, but for learning purposes, it's a bit involved because there's a lot of UI stuff. Good to do, but that's something I recommend doing offline. But what we're going to do here is, you remember when I drew the rectangle, here I'm just predefining the rectangle, and we're calling the grab cut algorithm for the first time using that rectangle method. And then that's going to give us, I drew a different rectangle this time as last time, but that's going to give us this image right here where you can see that it did a reasonably good job, but we can see this region of grass under here. So we need to give the grab cut algorithm more information in order to extract out what it is we really want. So the next important step is we're going to load in this file called messymask.png. I already included a sample, the one that I drew before that's in the data directory. At least it is as of today. If you download it before, it's not there. So this is something that I drew before. What is going on here? Okay. So that's something I drew before, but if you run this program below, at least the modified version of the program, it's going to save that mask to that file, so you can play with it yourself. So you load that, and then we're going to pass that into the grab cut algorithm. And instead of doing the rectangle initiation we did the first time, we're going to initiate it with the mask. And then this right here is the mask that was generated in combination with the rectangle and the first grab cut run. And then that's going to give us our output region here where we got rid of some of this background. It looks like in this case I still cropped off his hair because I didn't mark that as a region of interest. But you can play with that to your heart's content on your own time. So one other very powerful topic that we're not going to cover here, but I do recommend, is looking into histogram back projection. So I've included the link here. I do recommend reading up on that and running the code. All right, so slightly simpler topic, image transformations. It's very common that you're going to need to move your images to some new geometry. You need to scale it, you need to rotate it, you need to translate it, you need to do some combination, or you might need to do a perspective transform. Explain what that is in a bit. So transformations are pretty easy. OpenCV provides very convenient methods for doing this. So here you see kind of this big block of code, but bear in mind all this stuff right here, this is all just for display purposes. This is just for combining it. So all you really need to do your scaling is just this one line right here. So the cv2.resize command, where you pass it in your image, and then your scale factors, which can be anamorphic. They can be different in X and Y. And then the way you want to do the interpolation. So you can do, there's like cubic, linear, nearest neighbor. Cubic gives good results, but it's slightly slower. So if you're doing this on video or so forth, you might want to choose something else for speed. Now, of course, depends on your application. So we do our resize. So I did 2.5 here, and we can see the original versus the scaled version. And we can put in anything we want for that scale factor. So if you want to shrink it, it works exactly the same. We're going to do, now this is the original, this is the scaled version. Kind of looks like, we blew up the original, but if you look at the axis here, you can see that this has not changed size, but the scaled is in fact smaller than the one previously. So pretty simple. Of course, translation. Let's say you want to shift an image over. Again, very easy, although this one's a little less intuitive because before we had that CV2 resize function. Here we're going to use the more general transform method called warp affine. And just what an affine transform is, it takes in 3 points, 3 non-collinear input points, and then you specify 3 non-collinear output points. Then it will perform a linear transformation based on those points. So you can do translation, rotation, and scaling, skewing that way. But to do just translation, we're going to define the matrix manually here. So in general, it's a 3 by 3 matrix, but the bottom row is actually just 0, 0, 1. So we're just going to define the top 2 rows, where the last entries of them are the X shift and the Y shift. So you can put in whatever value you want here. And then for the x shift and the y shift, we define our matrix M, and then we're going to perform it on our image with that matrix, and we're going to specify the number of rows and the number of columns that we want in our output image. Now this may or may not be the same size as your input image. So you can see here we did the shift, we move x over 100 pixels, we moved y down 100 pixels, and now we got this blank region and we're cropping out the lower right hand corner. So that may or may not be what you want, but the option is there. You know, do you want to crop it, do you want to extend it, and so forth. Rotation. Okay, so pretty straightforward. This is the general way of computing a rotation matrix, but probably not going to want to do it that way for a reason that we'll get into. OpenCV does provide a convenient way of generating that rotation matrix, then feeding it in once again to the warp affine. So what we do, we specify our theta. This is a counterclockwise rotation in degrees. Then we plug that into our get rotation matrix 2D. And just exercise for the class. Does anyone know, can anyone kind of figure out what this is? Why am I passing in, you know, 1/2 the height and 1/2 the width? That's exactly right. Rotate around the middle. Because if you just rotate around 0, 0, that means you're rotating here, which probably isn't exactly what you want to do. So yeah, that will shift a lot of your image off screen. So probably more often than not, you want to rotate around the middle. So that's why we exchange, call it rows and columns here, but it's just the height and width in pixels. And then we pass that in, and then that will create the matrix that you need in order to perform that rotation about the middle. And once again, you can specify whether or not you want to preserve the dimensionality of the image, in which case you can see here we did a 45-degree rotation and we're cropping off the upper right and the bottom left. But of course you can extend this so that you are in fact keeping it all. So the general affine transformation, this is in case you want to define things in terms of your input points and your output points. I mean, this is generally what an affine transform does again. You specify your 3 input points. They do have to be non-collinear. If they're collinear, you're going to get a degeneracy and it's going to cause problems when you do your matrix algebra. So make sure both the input and output are non-collinear. And you specify the input points and the output points. Then you generate your matrix using the cv2.getAffineTransform. One thing I want to mention is remember that we do height and width when we're doing the indexing. This is actually x, y. So make sure you keep track of that. So you specify your x, y points, you generate your matrix, and then you call warp affine, using the same parameters as before, image, matrix, and output dimensions. And this will allow you to scale, rotate, translate, and even skew your object. But this, being a linear transformation, cannot do perspective correction. Perspective is, you kind of think of it the phenomenon where something that's further away is smaller in your image. So to do a perspective transformation, it's very simple. We're going to specify 4 input points and 4 output points. So we're going to use this image below, they just call it right.jpg, and I specify the input points just by inspecting this image. Then let's run this code again. So I got the upper left-hand portion of this book, the upper right-hand, lower right-hand, and lower left-hand, so in clockwise formation. So that was where these top points came from. Then these bottom points I just made up in order to get a rectangle output. So input points, output points, then you call cv2.getPerspectiveTransform in order to generate your matrix. And then just watch out this time, instead of calling warp affine, you call warp perspective, which is a little bit different. So then we see our results. So you can see that we took a picture of this object here, and now we have a head-on view that would make it easier to read. So this is just generally useful if you're trying to image a planar object that's off-axis, but you want to map it onto just a flat plane with respect to your camera for more analysis. Everybody's very quiet again, so assume everybody's happy, everybody's following? All right. All right, so moving on to the fun stuff. Well, more fun stuff anyway. So finding objects. So, okay, so very frequently in computer vision, we want to know if something is in our scene, and if so, where exactly is it? So first method we're going to talk about is template matching, which it's kind of the brute force way of seeing if an image is there. You start off with a big image, then you start off with something that, smaller image that kind of resembles the image that the object that you're trying to find. So the closer it is, the better. Then you're just going to slide it across, kind of like convolution, but it's a very similar operation known as correlation. You slide it across, multiply all the pixels together, and when there's a match, that correlation is going to be strongest. So you're going to get a 2D image where the peak is going to occur where the objects overlap. So this is effective, but just want to tell you the major caveat of this is it's very sensitive to perturbations, like it's sensitive to scale. You have to know that your object is roughly the same size as your template within the main image. And if it's rotated, then that's going to skew the correlation as well. So it can be useful, but it's very, very particular. So here's our example right here. So here we just show the different methods for doing cross-correlation. These are just different ways of computing. They're almost the same, but the metrics are a little bit different. So I do recommend studying up on that a little more if you want to understand them. But what we're going to do here is just show the results from that. So the critical lines that you want to know, you read the image. So I took the template right from the same image, so we're guaranteed to get a match. So we're using our soccer player Messi. I guess that's his name, right? Messi, I guess. And then we're taking a sub-image of that. So drew a rectangle right around his head. And then for each method, we're going to call this cv2.matchTemplate with a big image as our first parameter, the smaller image or the template as our second parameter, and the method as our third parameter. Iterate over all those methods, call it, and then what happens in this, like I said, the output is an image where low regions correspond to bad correlation or bad matching, and strong regions correspond to a good match. So this matching result window right here shows the result of the correlation, where you can see a strong peak right where the head is, which is exactly what it should be, and then it's just kind of noisy. Sometimes there are correlations anyway outside that region, but when it's done, when everything's working well, you should see a strong peak. And then we draw a rectangle where we detected that point, where Messi's head is. And then we can just see the plots for all of the different methods. And again, they're not exactly the same. So using this technique, the TM cross correlation, in this case, there was actually, you got stronger results here in the bottom right than you did where his face is. So you do have to be careful with your method, and what exactly the best one is will be application dependent. So just with computer vision in general, there's experimentation involved. You're going to have to play with methods and parameters to get the best results. But every other technique here actually worked well, and we found his head pretty nicely. All right, so this is something I've used a lot. This is the Hough Transform. So the theory behind this actually isn't all that complicated. So the Hough Transform in general is used for finding lines and other curves, things that can be described by parameters. The smaller the number of parameters, the more efficient it's going to be. So for example, let's say a line. That's one of the simplest ones. A line can be described with two parameters, just an angle and an offset. So to use this, what you're going to do is you're going to start off with a binarized edge-detected image. So we covered edge detection in the last one. So for example, you might want to run Canny on your image and then pass it to the Hough Transform. So what the Hough Transform does is it looks at the points in your edge-detected image and it compares them against your parameter space for your image of your curve of interest. So for the line, what it's going to do is you're going to try lines of various angles, various offsets, and then you're going to see how many of these edge-detected points actually line up with that line, how many actually fall on that. And you're going to get an output image, the Hough Transform space. So you're going to have your angle and distance from center or your offset. And when you have a lot of points that correspond to that particular parameter, you're going to get a bright spot. So here, for example, you've got your two line segments, and there are two very bright points which correspond to the angle and the offset of your lines. And in order to know whether or not you have a line there, generally you take a threshold. You look for a point that's greater than all the others. And the thresholding values are kind of free parameters, and again, it's experimental. It's going to be application specific what exactly those optimum values are. And this can generalize to other shapes. We're going to show circles. So you could, for example, explore a three-dimensional space of circles where you have the center X, the center Y, and the radius. And then you just see how many points here correspond to a given circle with those parameters. Then you'd have a three-dimensional space, you look for the peaks, and that's where your circles are. So let's see our example here. So we're going to show lines and circles in one demonstration. So we're going to read this image, aptly called stuff. So this is stuff. So we got a couple circular objects and a couple objects that have kind of line edges in there. And then we're going to go to grayscale because when you do edge detection, you don't use the color. Then we're going to perform our Canny edge detection, which we covered the last session. Then we're going to call the line transform as well as the circle transform. Circle transform has a lot of parameters. If you're interested in learning about that, I do recommend learning, using the documentation here. But here, I'm just going to tell you, where did I get these parameters from? I started from an example, and then I modified the parameters based on my image, my application. I don't know if there's any way of knowing, just humanly way of determining that beforehand, but just letting you know, yeah, I know they kind of look like magic numbers, and they kind of are, but they're empirically determined. The Hough lines is a little simpler because what you're doing here is just specifying the spacing between when you do the parameter sweep, you can only compare against so many different offsets, so many different angles. So you have to discretize your grid. So this kind of gives you the granularity of your grid. So say the lines are 1 pixel apart and the angles are 2 degrees apart. Sweep every 2 degrees, and we want to get at least 100 matches in order to determine whether or not we have a line. So very simple. The rest of this code is just for display purposes. I invite you to read that in your own time, but just these 2 lines of code right here will tell you where your shapes are. So we run the code, and then we can see here we found our circular objects, which are marked in green, and we found our line object, which is marked in blue. We can see that even though this lighter right here does have straight lines, we didn't find that because it was below the threshold. So I invite you to play with the parameters and see if you can get something where you can actually match the lines there and try to discriminate against spurious results here. So very useful. Very frequently you do have kind of regularly shaped objects that you're trying to analyze. So the Hough Transform is powerful when you do have that. And personally, that's come up a lot. So yeah, I do think the Hough Transform is particularly interesting. So suggested exercise, up to you if you do this. There's no grade or anything in this course, but provided an image here with circles, and my suggestion is you try to write a script where you count how many circles there are and what size the circles are, with which you can use to discriminate between the different kinds of coins. So if you do take on this exercise, you can write a script that will actually tell you how much money is in your image. Question?
So I'm curious how well this works on objects that are not quite circular. If you have like a football or something, say, would it like do what you'd expect, like kind of find an inscribed circle?
So that depends on your edge detection, it depends on your thresholding, and a bunch of other things. But what I will say is the Hough Transform can actually be generalized to any kind of shape that can be parameterized. So the Hough Transform has, for example, been adapted to detect elliptical objects. I don't know if OpenCV, to my knowledge, it does not have the generalized Hough Transform. You'd have to do that yourself. But the general algorithm is capable of doing it. As for whether or not, if you tried to do circles on a football-shaped object, I'm sure you could detect it, but you could also get a lot of spurious matches, because you'd have to lower your threshold and then it could match something else. So, whether you could do your own Hough Transform to detect your object, or you can do template matching, or, yeah. The thing about computer vision, there's no one end-all magic solution to everything, so you gotta do experimentation. All right, going through this pretty fast, actually. So, anybody else have any other questions? All right.
Question.
Yeah.
Let's say you have an image. Is there a function or a quick way to be able to put your cursor on and be able to tell what the pixel values? For example, when you were doing that perspective exercise where you had written in the coordinates, is there a way that you can draw out the coordinates other than just by looking at the image and saying, okay, that looks about, there is a readout?
Yes.
Okay.
Yes. And there are, Python does provide kind of a rich suite for doing interactive image analysis. So you could actually make markers here and print them out, but it would take at least a few minutes. But talk offline if you're interested in that. But yeah, I just use the readout in the interactive image to get those points.
Question.
Yeah.
So you mentioned it briefly earlier about the challenge of deblending and
Deblurring, deconvolution?
no, deblending. So you have two nearby objects, and let's say that they're whenever you do your thresholding to detect like regions above threshold, you have two objects and they form the contiguous region.
Yep.
Are you going to talk any more about how like what deblending algorithms are available in OpenCV, or?
Okay, short answer, I wasn't planning to talk about the deblending algorithms, but that's certainly something that we could talk about offline. So, I mean, a starting point would be look into the morphology algorithms. There's a lot of stuff just for that. You can see the CV morphology open. There are other things like anding them together, doing the dilation erosions. It's one of those things, there's no absolute way of, perfect way of doing everything, but yeah, there definitely are algorithms for it. I'll be happy to talk to you about it afterwards.
Okay, thank you.
Sure. All right, so let's talk about features. I mean, we've already been talking about features to some extent, but we want to talk about more general features that can kind of work on a variety of objects without necessarily knowing what they are ahead of time. So what are image features? Features are They define here in the document specific patterns or specific features which are unique, which can easily be tracked, which can be easily compared. So that's a very kind of lofty and ambiguous definition, but there are so many different kinds of features that you can use in an object that that's probably about the best definition that you can get. So we're going to talk about specific features such as corners first, and then we're going to talk about some of the more general features that you can apply to a wide variety of natural images to do detection and matching. So corners are simple to understand. Corners, when you have images that have objects with sharp edges, flat faces, and 90-degree or whatever angle, edges, then there are algorithms for robustly finding those corners and seeing where your boundaries are on those images and doing matching and transformations based on those. So the theory behind these algorithms is a little bit mathematically involved. It involves matrix algebra, determinants, eigenvalues, and so forth. So I would recommend reading up on those as well. But the nice thing again about OpenCV is that it just makes it so easy to use these, even if you don't know exactly how the inner workings of these they actually work. So two major corner finding algorithms are the Harris corners and the Shi-Tomasi corners, also known as good features to track. It actually calls it that in the OpenCV functionality. So yes, once again, we do have some magic numbers here, and these are going to be application specific. So these were found to work well for our given image, which is this blocks image, which is included in the OpenCV repository. So very easy, your output equals cv2.cornerHarris, your input image, and then your free parameters. And then that's going to output an image which is kind of 1 where your corners are and 0 elsewhere. And just for display purposes, we're going to dilate it and make it clear, and then modify our input image, make it RGB. So this is going to be blue where the corners are for Harris. Then similarly for the Shi-Tomasi or good features to track, we're going to call the good features to track with our input image and our free parameters. We need to convert it to integers in order to display it, and then we're just going to draw little circles using CV2's handy circle function in order to just put that in our image. And this is just display code. This is the heart of the code for actually doing the detection. Then we plot it, and you can see they both do a reasonably good job finding the corners. The Harris detector has more spurious points, but the Shi-Tomasi detector kind of missed a few of the corners. So Shi-Tomasi is a bit more rigorous when it comes to saying what a corner is, but you might miss something. So once again, application specific, depending on what you want to do. But the nice thing is, yeah, question.
They both seem to have missed some corners.
That's true. That's true. Yeah, it depends on the thresholding, and in general, I'm just going to show you a realistic case here. I could just show like a checkerboard pattern or something where it gets them all perfectly. But for any real image, there's almost always going to be some discrepancy. You're either going to get spurious results or you're going to miss some. It's hard to do otherwise. But perhaps with some processing, maybe with some filtering and some thresholding, we might be able to do a better job here. So this was just the image that they included here, but a suggested exercise for you, try to do some processing and see if you can get a 100% no spurious, no missed corners match. But yeah, good point. I'm just going to comment in general on computer vision. It's not magic, There's been a whole lot of progress here, and it's amazing what they can do, but there are no magic algorithms that are just going to figure out exactly what you want and work perfectly every time. You have to do experimentation, you have to try different parameters, and then it might work great for a given set of images, but then you try it on something else and won't work so well, or it might even fail spectacularly. But yeah, so yep, just I definitely recommend trying this on different images. You know, this is a nice one to start with, but yeah, try to find some images with corners in there and play with these and try the different parameters, try to make it work. And of course, if you can apply this towards, you know, your actual work applications, all the better. All right, so fun suggested exercise. Find or create an image that contains a rectangular object. Could be like the front of a book like we saw before, or could be a table face or whatever. You know, something that's captured at an angle. You know, for simplicity, I recommend using a high contrast background. Then I suggest you try to write a script that finds those corners and then performs a perspective transform to bring it into the head-on planar view. So that will test your ability to use both Harris detectors and the perspective transform. All right, so we're in the last part. So the last thing I want to talk about are, you know, general features which don't necessarily correspond to any corners, but they just correspond to things that, you know, are somewhat unique and identifiable about an image, something that can be used to discriminate and to match. So there's a wide array of these things, you know, with different names, different acronyms, and each one of these has a lot of theory involved. So, you know, no possible way you can possibly do any justice to the theory here. But if you are going to use these, I do recommend reading up on them. You know, Wikipedia, as always, has great tutorials, as well as docs.opencv.org. So the nice thing about these features in OpenCV is that they behave very much the same. So we can do experiments on an image and just kind of interchange them and not have to just modify all of our code to do different things. So we're going to do a feature matching homography demo. Homography just means the mapping, like the perspective mapping between one image and another. And using the features that we match, you can compute that pretty robustly. So this is our demo. So you know, we're going to read in our box and scene. So what that is this box right here and the scene that contains it. So again, I invite people to play with each one of these. So what you want to do is uncomment just one of these lines. So you can do SIF, SURF, or Bakaze, or Brisk. And the thing I want to mention about SIFT and SURF is that those are proprietary algorithms. They're not strictly free and open source. Depending on which version of OpenCV you have and where exactly you got it from, you might not even have SURF and SIFT. For the Menpo repository that we pulled from, we do have it. But you know, if you're using OpenCV version 3, it's not in there by default. Also, this code right here, if you are using OpenCV version 2, they're located in a different location. So if you see some older code and you're trying to use it with OpenCV version 3, you have to modify it accordingly. Otherwise, you'll get an error. But you know, SURF and SIFT are great algorithms. You might need to use them, but if you are using them for, like, say, a commercial purpose, you're actually supposed to pay for them. So it's up to you to decide whether or not it's worth it. But we have a variety of other features that are in fact free, that are in fact open source. So you know, I recommend playing with them all and just find the one that works best for you. So we'll start off here with Brisk. That stands for Binary, Robust, and Variant Scalable Key Points. Yeah, so I don't think that really tells you much about how the algorithm works, but it sounds neat. So we define our detector, and you know, again, you can assign whatever. They all work pretty much the same. They all have this detect and compute function built into them. So we run detect and compute in both the input image, the big image, the one that's in the scene, as well as the query image, the object that we're trying to find within there. And the idea is, if everything's working well, you should see every one of these features. Not only do you have like an XY point, that's a point of interest, but you have something that's called a descriptor, which is a numeric vector that tells you something about what's there, like is this corner-like, is it line-like, or so forth. What exactly it is depends on what the detector is, and it varies, and it's a little complicated, but fortunately it's not complicated to use. So we detect our key points, and then once we have the key points, we want to find which ones match up with which ones. And in general, not all key points are going to line up identically. It's not like there's a one-to-one mapping. And you might find some matches where something in one image is going to go to a completely different point in your output image. But the nice thing about that is that OpenCV provides matcher methods. So we're going to use here the brute force matcher, which is not the most efficient matcher, but it is robust. There's also the flan matcher, which you can call this very similar. It's like cv2.flan matcher. Straightforward, but we'll use the brute force matcher here for simplicity. And what we do here is we pass it in the descriptors. And when you have enough descriptors that actually match, this will actually output the pairs of matching coordinates, the pairs of matching features and their descriptions. So you can know how it maps from one to another. And then, again, not all of the matches are going to be good. It will do some spurious matching. But if enough of them match so that you can find a good mapping, what you call the homography between one space and the other space, you're trying to find a perspective transform, a matrix or a set of 4 input points and output points. Conceivably, you only need 4 points. But we have more than 4 points, some of which are going to be bad. So we're going to try to find the best set of points where you find a reasonable homography, a reasonable mapping between one space and another, and we're just going to reject what we call the outliers. So yeah, there's definitely there's an algorithm behind that, and once again, I do highly recommend looking into it, but again, OpenCV just makes it nice and easy. So we look at our matches, and then all this code right here, it discriminates between the good matches and the bad matches. Make sure that we have enough good matches to actually do the homography. Then we're going to draw lines between the input and the output, which we can see here. So in this case, it did in fact work pretty well. And I believe for all of these cases right here, let's do like orb, for example. So it finds fewer matches, but it's still enough to determine homography. If you want to inspect this better, this is very similar to the included find object Python script that's included in the repository, and then we can actually highlight these and see what's mapping where. So you can see right here, this red line corresponds to a spurious match, but all these green lines correspond to actually good matches, where you can see that it did in fact find the corresponding points. So I think right here, use the brisk method. So this is powerful stuff, but again, it's not magic stuff. You can't expect this to work super reliably just for anything that you throw at it. So definitely going to be some experimentation, and I do recommend trying this on your own images offline.
Would it still work fine if that image on the left was vertical?
Yes. Yes. These are rotation. I'm not sure all of them will, but in general, these should be rotation and scale invariant. So they do work better than corner detectors in that sense. So I actually went through this pretty quickly. It's just a little before 1 o'clock. Does anybody have any questions?
We've been taking all of our data from images, and so what can you say about cameras and camera support?
You mean you're asking about videos?
Yeah.
Oh, well, good question. We are going to cover videos in some detail in the next session. Yeah, the next session, if we look at the syllabus, yeah, we're going to cover video analysis, and just a little bit of whirlwind tour of machine learning. So yeah, this one was a little bit short, but hopefully this was interesting and exciting, and you guys will be able to apply this towards your own projects. Any other questions?
So are these sorts of algorithms, is this what's used for face detection?
So the question is, are these used for face detection? Conceivably, in the next session, I'm going to talk about Haar cascades, which is a little bit more of a robust method of face detection. So these features, they could actually be used for machine learning and general object identification. And with machine learning, for supervised machine learning, you have a set of trained images, and images that you say like, okay, this is a face, this is a bird, this is a car, this is a train, and so forth. Then you want to identify it. These features are a good way of kind of doing what's known as a dimensionality reduction. So rather than just feeding your algorithm like neural networks or support vector machines the entire image, which has high dimension, you can feed it a list of features and descriptors. And they do get reasonably good results in actually identifying images and identifying objects. Just FYI, like what's currently in vogue is, you're familiar with deep learning? Okay, yeah, deep learning is where you have like, really complicated neural networks, and that's getting the best results to date, which is actually like performing as well as humans, but it requires a lot of computational power. So we're not going to do that here. OpenCV will see a little bit of the machine learning capabilities in the next session, and like how to work with Haar cascades for doing detection such as human faces. Question?
What about using OpenCV for like reading text or that sort of thing? Do you end at a template of like, this is what's written in this image, and then like how would you go about doing something like that?
Okay, so the question is that can OpenCV be used for text analysis? So I personally would not use OpenCV for text analysis. The tool that I would recommend is Google's Tesseract, which has Python bindings in it, and that's a powerful way of telling what text exactly is in your image and where it is. So I don't know, maybe somebody's done something in OpenCV, but I would recommend a dedicated product for that, like Tesseract.
So this is mostly for recognizing objects and that are not like text or something uniform?
Well, it could be used for text. I mean, like we're going to do some digit recognition in the next session. But how do I answer that question? It's just OpenCV is kind of general purpose, whereas there are dedicated tools for that. So I mean, OpenCV can do like a huge number of things. Kind of talked about in the first one. For recognition is a big one, but just doing general image processing, blurring, edge detection, just scientific purposes, extracting regions of interest, and it can be used for like stitching images together, like doing the panorama view and so forth. Lots and lots of other things. But if you're doing like a specific application, you're talking about was OCR, optical character recognition. My recommendation to you would be to use a dedicated product for that. Otherwise, I'm sure OpenCV could be used to do it, but to the best of my knowledge, it doesn't have nice built-in features for it. So it would be a lot more coding on your end if you were to try to do that. Any other questions? All right, well, thank you, everybody. I look forward to seeing you on Thursday for what I think is probably the most interesting session, where we work with videos and do machine learning. I appreciate the applause.